Hey everyone, welcome to Insights by Rish. In today's video, I am going to implement a machine learning project of Titanic Survival Prediction using Logistic Regression algorithm. Now for this particular project, you can download the dataset for Titanic Survival from any online source like Kaggle, or you can import the built-in dataset from the Seaborn. So for this project, I am going to import the built-in dataset of Titanic Survival from the Seaborn, and let's begin. So for the first stage, let us import all the necessary libraries that we require. So importing libraries. So first we will import pandas. We require that to create data frames. Then we require matplotlib. Then we require Seaborn. Then we also require NumPy. Whenever we are handling the outliers, in that case we might require NumPy there. So import NumPy as NP. Then we will import the train test split here. So from sklearn.model selection, we will import train test split. Then we are using logistic regression here. So from sklearn.linear model, we will import logistic regression algorithm. Then we'll also import various evaluation metrics of logistic regression here. So from sklearn.metrics, we will import the accuracy score, then the confusion matrix, and then the classification report. Then we will also import the simple imputer here to handle the missing values from the dataset. So from sklearn.impute, we require simple imputer. Then we will also import the min-max scaler to normalize our data. So from sklearn.preprocessing, we will import min-max scaler. And then it might happen that our dataset is imbalanced, and for that purpose we might require the SMOTE technique. SMOTE basically is an oversampling technique where we increase the number of samples of the minority class. So from sklearn from imblearn oversampling, we will import SMOTE. Let us run this cell. These are all the libraries that we require throughout the project. Also we also need to import the warnings here, because we need to handle the warnings that Jupyter Notebook gives us every time. So import warnings, and then warnings.filter warnings. We will ignore all that warnings. Now we will load the Titanic dataset from the Seaborn. If you want to check what all dataset Seaborn has, so you can do something like this: sns.get dataset names. And let's run this. So these are all the datasets available in the Seaborn library, and from this we are going to import the Titanic one. So we'll say df is equal to sns.load dataset, and we'll import Titanic. Let's run this. Let us try to display the first few rows of the df using the head method. So this is the dataset that we have, and the first column, that is the survive feature, is our target feature. That is what we want to predict, and remaining all will be our input features. Now in this dataset there are many garbage columns, that is there are many columns that we don't require, like check the column who and adult male. This is the column basically they are conveying whether the person is female or male, but we already have that information from the gender column itself, so we don't require these columns. Also, we don't require the deck column, we don't require the alone column or something like that. So we will delete all the unnecessary columns that we don't require. Let us first print the column names. These are all the columns that we have, and we'll start dropping the columns. So the next task is dropping the unwanted columns. So we'll say df.drop columns. And here you will provide the list of all the columns that you want to drop. The first column that I want to drop here is SIBSP. The next column I don't require is Parch. Then Embarked. Then Who. Also we don't require the class column, as we already have the passenger class in the P class column, so we don't require the class column as well. Then the adult male, and then the who column. Okay, I have already mentioned that. Then the deck column, then alive. We don't require this alive column because that is what we are already predicting, that whether the person survived or not, so we don't require the alive column. Now we might require the alone column because it's basically saying that whether the passenger was alone or whether he was accompanied by anyone. So we will keep that, and these are all the columns that we don't require, and basically we are going to delete it from the dataset. We'll also mention the attribute in place is equal to true in order to make this changes permanent. Let's run this and let us again check the data frame now. So now these are all the columns that we have. Apart from survived, all other columns are our input features. So this is what we require. The next task that we want to do after dropping the columns is we want to check for any missing values, like if any dataset consists of the missing values. So we'll say checking missing values. So to check the missing values, we'll say df.isNA.sum. And when you take the look at the values, you find that there are some missing values in the age column. There are around 177 missing values in the age column. Now there are multiple ways to handle these missing values. Either you can fill it with 0, either you can fill it with the mean of the column, with the median of the column, or you can drop them. You can just drop them. But you can only use the drop method when you have a very large data sets. Like dropping 177 rows won't affect. But when you have very small data sets, like the shape of this particular data set is 891, it just consists of 891 rows, and if you drop this 177 rows out of 891, you will have a very small data set, so your model won't learn anything actually. So instead of dropping the rows, we will perform imputation on this. We will replace the empty values, we will replace the missing values from the age column with the mean of that column. So we will say, so we have already imported the necessary library here. We have already imported the simple imputer from sklearn.impute. We will use that. We will create an object of impute, that is simple imputer, that is imputer. We will say simple imputer, and we need to specify the strategy with which we want to replace the missing values. So here the strategy with which I want to replace the missing value is a mean. So I will say mean. And then I need to explicitly mention the column where I want to do all this manipulation and changes. So I will say df age column is equal to imputer dot fit transform. You can do this thing separately. You first use the fit method and then the transform method, but I will do all these things in a single go. So fit transform, and here I will say df age. Now the reason behind supplying two square brackets here is if you just supply a single square bracket here, in that case it will consider your age column to be a one-dimensional, and it requires 2D array for processing, and hence we have provided it with the double square brackets. So let's run this and let us now again check the missing values. So now we don't have any missing values in the age column, but we have some missing values in the embarked column, and I think embarked town column. Now the embarked town column is a categorical column, so you can't basically fill it with any imputation function. So we'll drop that row. So we'll say df is equal to df dot drop na. Let's run this and let us now check the shape of our data frame. So now we have 2 rows less, as we have deleted the 2 empty rows of embarked town. So let us display the data set again. This is our data set. Now that we have handled the missing values, the next thing that we want to do is we want to check that whether this data set consists of any outliers. So to check, we cannot check for outliers for every column. So we'll just first use the describe method here. And then when you take the look at this describe, when you take the look at the statistical analysis using the describe method, you just check for the values at the 75% and at the maximum. If you find a drastic difference between the values present at 75% and at the maximum, then you might assume that that particular column consists of outliers. Now for the survived and passenger class, your 75% value and maximum value are same. Same goes for age, not a drastic difference, like 35 and 80 will still go. But for fare column, you might find that, see, at the 75% you have the value 31, but at the maximum you have the value 512. So between the 25%, there's a drastic exponential growth of the fare value. So your fare column consists of outliers, and to visualize that, you will use the Seaborn box plot. So we'll say SNS dot box plot, and you will supply the DF fare column there. Let's run this, and as you can see, it consists of outliers. The dots that you find in this particular graph, the circular patterns that you are finding here, are actually your outliers, and you need to handle this outliers. To handle this outliers, we have multiple methods. You have z-score method, you have percentile method, standard deviation method, IQR method, but here you will use IQR method because it's efficient and it requires less time. So we'll say we will use the IQR method for handling outliers. So let us start with saying quartile 1. Now in this box plot, you have quartiles, quartile 1, quartile 3. The lowest fence is your quartile 1 and your upper fence is your quartile 3. And then the upper line, the upper black line, is your maximum value, and anything exceeding that is considered as an outlier. So we'll say quartile 1 is equal to NP. NP is an alias of our NumPy library. So NP dot percentile, the column which consists of outliers, which is the fare that you will supply here, and then the quartile 1 consists of first 25% of data, so you will say 25, and then interpolation is equal to midpoint. In a similar manner, you will build your quartile 3 as well. So you will say quartile 3 is equal to NP dot percentile, and here you will just change 25 to 75. Your quartile 3 consists of 75% of data, everything else remains same. Then you will write the formula for IQR, which is quartile 3 minus quartile 1, and then you will set the thresholds. Now here in your IQR method, you cannot randomly set any threshold values. You have a formula for that. So you will say your lower bound, or you can say your lower threshold, is equal to quartile 1 minus 1.5 into IQR, while your upper bound is equal to your quartile 3 plus 1.5 into IQR. These are your threshold values. Like anything greater than your upper bound and anything lesser than your lower bound will be considered as outliers. And next, we will say we only want the instances that are present between the upper bound and lower bound. That is, the instances where the value of the fare column is lower than your upper bound and greater than your lower bound, will only include that particular instances. So you will say df is equal to df, where your df dot fare is greater than your lower bound, and your df dot fare is lower than your upper bound. Let's run this. Let us now check the shape of our DF. Initially you had 889 rows and now you have 775 rows. So the rows which were outliers are now deleted. So let us try to visualize it again. Let us try to visualize this box plot again. Now you can see we have very less number of outliers now. Here our box plot was actually suppressed due to the all outliers, and we handled maximum outliers. Now there are few outliers, but we can't do much because we already have the predefined formula here. So now that we have handled the outliers, the next thing that we want to do now is to convert the categorical values into the numerical ones. So you have the few columns here, like the gender column, the town column, or the alone column, where the values are stored in the categorical fashion. And in order to process and in order to supply it to the machine learning model, you need to first convert it into the numerical way. So to do so, depending upon how many categories you have, if you have 1 or 2 categories, you will use the replace function, and if you have more than 2-3 categories, then you will use one-hot encoding to convert the categorical into the numeric ones. So let us first check the unique categories from the gender column. So you will say df.sex.unique. Let's run this, And so the unique values into the gender column are just male and female, so just two unique values, and hence you will use the replace method here. So you will say df dot sex dot replace. You are going to replace the value male with 0. So whenever you encounter the value male, you are going to replace it with 0, and wherever you encounter the value female, you are going to replace it with 1, and then you will provide an attribute in place is equal to true in order to make the changes permanent. Let's run this. Now let us again check the unique values from the sex column, and you might find now the values are 0 and 1. The next categorical column that we have here is embark town. Let us check the values for embark town. So we'll say df dot embark dot unique. So here we have only 3 unique values again for embark town and not more than 3. So we'll again use the replace method here. So we'll say df dot embark town. So you will use embark town dot replace, and wherever you encounter the value Southampton, so you will say Southampton. So wherever you encounter the value Southampton, we'll just copy paste it from here. You will replace it with the value 0. Then whenever you encounter the value Queenstown, you will replace it with 1. And wherever you encounter the value Shabok, you will replace it with 2. And then we will say in place is equal to true. Actually, it should be inside the parenthesis. Let's run that. And let us now check the unique values from the embark town column. Now it will be 0, 1 and 2. Now the next categorical column that we have here in this particular data set is the alone column. We will check for the unique values from alone column. We have just 2 unique values like false and true, and hence we'll use the replace method here. So we'll say df dot alone dot replace, and wherever you encounter the value false, you are going to replace it with the 0, and wherever you encounter the value true, you are going to replace it with 1. And let's say in place is equal to true. Let's run that, and let us now check our data frame, the first 5 rows. So now except for alone, all other things okay. So the alone column is not yet replaced because the false and true aren't the string values, they are the boolean values, and hence we need to remove this single quotes. Now let us run this, and now the values are replaced. Now that we have replaced the values, the next thing that we want to do before performing the data normalization here is we'll check the whether the data set is balanced or not. So we'll say df dot survived, which is our target feature, dot value counts. Let's run that, and you have 512 instances for the label 0, and you have just 263 instances for the label 1, which means your data set isn't balanced. So the next thing that you want to do is you want to balance this data set, and you will use a smooth technique here, which is an oversampling technique where you oversample your minority class. So you will say, so before performing this mode, we will just divide our data set into the input features and the target feature. So in our X, we will say df dot drop columns is equal to survived. That is, we want to include every column into the X data frame except for survived, which is our target feature, and then Y is our target feature. We will say df survived. Let's run that, and now let us again try to display the input data frame, which is this is our input data frame. Next, now we'll perform the smooth here. So we'll say sm, which is an object of smooth class. We'll say smooth, and the sampling technique that we are using here is minority, which means we are oversampling the minority class. We are trying to increase the samples of minority class. In this case, the minority class is the class 1 because it's having a very less samples compared to the class 0. So minority, and then we'll say x comma y is equal to sm dot fit resample x comma y. Let's run that, and let us now try to check the shape of our x Now we have 1024 rows. Initially we had around 700 rows, and now we have 1024 rows, which means we have increased the number of minority samples. Now that we have also balanced our data set, now if you try to check the value counts, now the values are stored in y, so y dot value counts. Now you have equal number of sample for both the categories. So the next thing that we want to do here, now we want to perform data normalization. So when you take the look at your input data frame, you might find that every column is on a different scale, and hence you need to normalize your data. So we'll say scalar is equal to min max scalar, and then x is equal to scalar dot fit transform. We are doing it in a single go. You can also do it individually, first the fit method and then the transform method. So let's run that, and let us again try to display our input data frame now. Now all our data is normalized, all our data is scaled between 0 and 1. This is what we want. Now we are done with data pre-processing steps. We want to divide our data set into the training and testing set now. So we have already imported the train test split model from the model selection sklearn. So we'll say xtrain comma xtest comma ytrain and ytest is equal to the train test split. We will provide our input features which are stored in x, and the target feature which is stored in y, then the test size which is 0.2, that is 80% data in the training set and 20% data in the testing set. Then random state is equal to 42. Let's run that, and let us try to check the shape of our xtrain and ytrain. So we'll say xtrain dot shape and xtest dot shape. So the training set now has 819 samples and the testing set now has 205 samples. Now if you try to check the value counts in the ytrain and ytest, so let's say ytrain dot value counts, and let's say ytest dot value counts. So you can see the value counts are balanced. The difference between your instances of class 0 and 1 in your training set are equal to the difference of instances in the testing set as well. So you don't require stratify methods here. The next thing that we want to do is, now we will actually start building our model. So we will say model is equal to logistic regression, and then we will fit it. So model dot fit, we'll fit the training set here. So xtrain comma ytrain y underscore train. Now that the model is fitted, we will try to make some predictions. So let's say model dot predict the values for x test. So these are the predicted values, and we will store that into a variable called pred. Now let us try to compare the original values and the predicted values. So we will try to display the first 5 true labels here which are stored in ytest. So the first 5 true labels are 0, 1, 1, 0. This basically means that the first person died while the next 2 survived, and again the next 2 died. Let us check what our model has predicted. So we'll say pred the first 5 instances, and you can see the prediction is slightly different from what we had in the true labels. Everything else is same. Just for the third person, or just for the fourth person, the model is predicting that the person survived while he died. Now let us try to check the accuracy of our model. We have already imported the accuracy score from the metrics. So we will say accuracy score, and here we will pass our true labels which are stored in ytest and the predicted labels which are stored in pred, and we will multiply it by 100 as we want our accuracy to be displayed in percentage. So our model is giving us an accuracy of 81%. Now we will try to print the classification report. So we will say print classification report, the true labels which are stored in ytest and the predicted values. Let's run that. This is a classification report, and when you take the look at your F1 score, your F1 score for both the classes, like for class 0 and class 1, is almost same. This is because we handled our imbalanced data set. If we wouldn't have handled our imbalanced data set, then in that case the difference between the F1 score of both the classes would have been drastically different. and hence we are getting an accuracy of 81% and F1 score is almost same for both the classes. Next we'll try to print the confusion matrix. So we'll say CF is equal to confusion matrix. We'll pass the true labels stored in whitelist and the predicted labels, and then we'll say normalize is equal to true. Now we'll plot the confusion matrix using the heat map. So SNS dot heat map. You will pass your CF variable here. You will say N0 is equal to true, as you want the values to be displayed on the confusion matrix grid. If you don't want your values to be displayed, you can set N0 is equal to false. And then the theme of your heat map. So I will say CMap is equal to crest. This is the theme of our heat map. Let's run that. And this is our heat map. Let us try to make it more readable. So we'll label it. We'll say plt.xlabel. The values on the x-axis are the predicted ones. So we'll say predicted. And values on the y-axis are actual. So we'll say plt.ylabel actual. And we'll say plt.title confusion matrix for Titanic Survival Prediction. Let's run this. And now this is our confusion matrix. What it is saying is 83% time it's happening that the original label is 1 and your model is also predicting 1. That is originally the person survived, and your model is also saying that the person survived. And 80% times it's happening that originally the label is 0 and the model is also predicting it to be 0. That is 80% times the person died and the model is also predicting the same. Just 20% times it's happening that the person actually died but the model is predicting that the person survived. And just 17% times it's happening that actually the person survived but the model is predicting that the person is dead. So this is how you basically infer your confusion matrix. And that was the project for Titanic Survival Prediction. You got an accuracy of 81% for this particular. That's it for the video. Thanks for watching.